This is session 4AP, so when you're entering your feedback, please use that session code, and there'll be a reminder of that code at the end as well, along with a QR code. So we've got Joe Winchester from IBM, who's going to be talking to us about software in space and what mainframes can learn from space missions. So this is also being recorded and will be available after the conference. And if you can all make sure you ask some questions in the chat window, and I'll ask them to Joe at the end as well. So thank you, and over to you, Joe.
Cool, thanks, Sophie. Just to check, you can still hear me?
Yep. Excellent.
All right, okay. Awesome. So thanks so much for joining this session. A little bit of background for this session. That's a picture of me, and I just had to update my Twitter handle. It now says I'm a 55-year-old nerd because I was 54 until a month ago. So I often like the fact that when you go into Twitter or social media and hook up with work colleagues, often you find they're interested in other things outside of work. I'm interested in lots of things outside of work. One of them is astronomy. I like to do a little bit of amateur astronomy. And I also hang out with astronomy clubs. And when I go to the internet or watching sort of, TV shows, I love everything related to astronomy. And when GSE was face-to-face, one of my favorite talks to attend, if any of you ever get to go listen to Mark Nelson, he gives a very, very good talk called Mainframes and the Moon, I think it's called. And he always gets Best Speaker Award, and he thoroughly deserves it and things like that. So this is a little bit different. It's not about my day job, which is working with open source software tooling. It's about sort of space missions. I've given it once before to an astronomy club who enjoyed it. This is the first time I've given it to mainframers. So please let me know if you think it sucks, if there's something I'm missing, or if you want to start having a discussion about it. Okay, there's the session number, there's the barcode, as Sophie said. You can scan that when you wish to go to and give me 5-star feedback at the end. The GSE conference charity raffle for this slide here. Again, I think it's on every single presentation. GSE is a charity, and you can donate, and the supporting charities this year are the lifeboats and I think a pet charity. I think that's a little paw print there. Okay, so I've certainly donated. I've donated the lifeboats already. I'm a big. Okay, so let's get into the talk. So what I want to do, this talk is kind of it's didactic. I'm going to delve into 4 particular space missions, and the background to those missions. We're going to geek out a little bit on that, and then how they relate to software, because all of these missions, well, I won't spoil the ending, you might already know what happens with these missions, but all these missions kind of think they either spectacularly fail or are spectacularly rescued. There's some incredibly innovative things that go on with those missions. And I think it's just interesting, and we'll tie them. So the first one we're going to start is Ariane 5. So a little bit of background before we go into Ariane. So Ariane is, okay, so let's look at this picture. Here's good old planet Earth. And in 1957, the very first satellite was launched. It was launched by the then Soviet Union, and it's called Sputnik 1. And it just sort of orbited the Earth and kind of beeped, and people listened to it. And it really started the space race to put stuff in space. Between 1957 and now, there's now actually about 3,000 satellites in space orbiting the Earth. And there's actually about 8,000 as well, either dead satellites or junk satellites. So it's a very busy place. The junk satellites are actually, some of them just die, some of them bits fall off, and a couple of them have actually been deliberately exploded. Both China and India, as a sort of precursor to space warfare, I think, actually basically blew up satellites. They launched something whose purpose it was to create a space explosion, but all that debris is still floating around in space. And if we look at, so what you've got is you've got a massive race to basically put that stuff into space. When things go into space, they go into different orbits in space. There's what's called the LEO, or the low Earth orbit. The low Earth orbit is the one, it's very close to Earth, actually. It's no more than 1/3 of the radius of the Earth. It's where recently, I think Jeff Bezos went into space, and Richard Branson went into space, and there's a big debate about did they actually go into space. What they did was, once you enter the very inner low Earth orbit, you can achieve weightlessness. And when a satellite goes into that Earth orbit, it actually rotates. You actually get about 11 orbits of the Earth a day. So a satellite goes around the Earth about 11 times a day, so perhaps once every 2 hours. And that's where telecommunications satellites tend to sit. It's where GPS satellites tend to sit as well. GPS satellites tend to sit, sorry, slightly further out because global positioning. Spy satellites tend to sit in here. There's a particular orbit, which is where if you've got the sun behind you, because if you think about the Earth rotates sort of 24. They stay in that orbit, and then that's all the spy satellites, because they're in the area where the sun is constantly lighting and stuff like that. So there's a lot of stuff in that orbit. That's where most things are. Low Earth orbit. Then you have what's called the global positioning satellite, the GPS. This is a geostationary orbit out here. The GPS orbit is once every 2 times. So 2 times a day, a GPS satellite will go around the planet. And the geostationary orbit is a lot further out. We're talking about 20,000 kilometers here, about 36, almost coming up to 40,000 kilometers, versus about 2,000 kilometers. So what you're trying to do is you're trying to basically put something on a rocket and get stuff into that orbit, okay? The geostationary is where you will have a satellite that you can point, and it maintains the same line of longitude of the Earth. So with the Earth, you have longitudes, which go from north to south, latitudes, which go from, so north to south is sort of join up, yeah? Longitudes and 0 for the equator. UK is kind of about 50 degrees longitude and stuff. Okay, so you're trying to maintain that position. So if you point something into space, like you have your satellite dish outside your home, or you're sending a television picture back and forth, the satellite's up here. It's a lot further, so it's a lot. You actually get a delay with light bouncing back and forth. A little bit of background orbits. Now, the space race is really, how do you get stuff into there? So NASA had a very successful reusable spacecraft called the Space Shuttle, which very, very successful. Unfortunately, had 2 missions that didn't work. Those were based on hardware failures rather than software failures. Tragic loss of life in both of those missions. But NASA actually had very, very reliable software getting their stuff into space. By the way, coming back to here, nobody has gone outside, no human has ever gone outside the low Earth orbit since the Apollo mission, the last Apollo missions happened. Obviously, the moon is way over here somewhere. Okay, so Ariane is built by ESA, built by the European Space Agency. It's a consortium of UK, France, sort of French technology in it as well. It launches out of a space, French Guiana off the coast of Africa. And Ariane 5 is the mission that I'm going to look at now. Ariane 5's maiden launch. So as Ariane 5, as its name implies, was the 5th incarnation of the rocket. So Ariane 1 was actually about 15 years earlier. And then there was Ariane 2, Ariane 3, Ariane 4, Ariane 5. And throughout the sort of decades this was progressing, they were basically upgrading the technology to get more stuff into space and heavier stuff into space. So this particular maiden launch, they were putting 4 satellites, but they were uninsured in brackets, into the low Earth orbit. So quite close to Earth, okay. Ariane 5, so Ariane 4 rocket, which was the last launch of the rocket before they upgraded it to Ariane 5, that could basically put about 5,000 kilograms into the low Earth orbit. Ariane 5 could put about 20,000 kilograms. So this is 4 times as heavy a payload. So to do that, you've got something that's got 4 times as much poke, right? This thing has to get into get to escape velocity before you can dump. You have to get your satellites into escape velocity. The way escape velocity works is, if you think of the sort of Earth is a very gravitational body, if you fall to Earth, you will just basically burn up through the atmosphere, or possibly bits of you will actually get through to Earth if you can withstand the sort of friction from the atmosphere. Escape velocity is your perpendicular velocity that you need to be traveling. And so if you think of a triangle, if you're falling to Earth, being pulled into Earth, but you're going sideways as well. So you kind of go sideways and then get pulled down. And the triangle basically gives you an orbit escape velocity. So things are trapped. So when you see rockets go up, they sort of start going up and then they go sideways like that. And that's because what they're trying to do is they're trying to get into an escape velocity orbit. And then once you hit escape velocity and you're flying along at escape velocity, then you basically dump your payload. Then you just drop back down, and either bits of your rocket will burn up, or hopefully bits of your rocket can actually come back in and be reused. And there's a lot of great stuff going on with SpaceX at the moment, things where they actually land that stuff in a very kind of Tintin and space way for people who know. Anyway, so let's go and have a look at how this mission works. So I've got a little bit of a video clip here. So the rocket is in French Guiana. It's going up, and awful lot of fossil fuel being burnt there. Starts tilting ever so slightly, because rockets do, they go up, and then once they get past a certain height, they're going to start to tilt. And it tilts over a little bit, and then it blows up. Why did that happen? And what so here's some pictures of it, just in case that video failed to play. It's just ones and zeros. I was watching a film the other day. What was it? It was Free Guy. Actually, a very good film, Free Guy. It's got Jodie Comer in it, who I absolutely love from Killing Eve, if any of you have watched that TV series. It's got Ryan Reynolds, who, you know, is amazing, and some Deadpool and everything that he's done. And it's a very, very cool movie. Anyway, it's really, really good movie for Chef Free Guy. There's a bit in Free Guy where somebody says, they're talking about writing code, and they say it's just ones and zeros. And I love that kind of Hollywood life. It is. Code and numbers are just ones and zeros. So most of us here probably mathematically know what binary numbers are. So if I'm looking at the number binary, you have effectively the way you encode numbers is you, in hardware as well, in chip hardware, is you have transistors, and transistors can either be, you know, high or low charged, or not charged, polarized or not polarized. So for example, you know, you have 1, 2, 4, 8, you know, so on, you know, you're basically doing the powers of 2, right? And once you max it, add 1, and then that overflows, right? And that's how you store the number 10. So if you have an 8-bit computer, something that can basically count in 8 bits, the maximum number you can store is all of the ones, which is 255. Okay, you can actually store 256 numbers, because 0, if you count it as a number, gives you the 256. Right? Some people think that 0 is not really a number, but we're not going to have that quarrel right now. The maximum number you can store in a 16-bit computer in a register is 65,536, also commonly just rewritten as 64K. It's a lot easier to conceptualize it as 64K. 64-bit computing, you can store much bigger numbers. I mean, that's as good as infinity, right? It's just sort of, you know, millions, American billions, English billions, trillions, you know, a big number, right? So once you get to 64-bit computing, you can, you know, sort of count the number of grains in the universe. We're talking about very, very large numbers. Now, what's happening throughout the progression of Ariane 4 to Ariane 5 is you're going through the shift between sort of 8-bit computing, you know, the sort of Zilog Z80 chips, to 64-bit computing. Right now, you're sort of Intel, you know, Pentium processors, and, you know, the i3s and the i5s and i7 stuff, they're all 64-bit, right? The ARM7, they're all 64-bit computing. But back in the 1980s and early 90s, you had 8-bit computer, where basically that was the sort of apex predator. So the 286, the 386 were 8-bit architectures. So 286 was 8-bit architecture. I think 386, 486 were 16-bit architecture, and the Pentium was 64-bit. So, and the same is also true with mainframe computing as well, right? It's if you deal with things like kicks, you know, things go forward. You start moving towards 8. You go from 16-bit to 64-bit. Now, the problem that Ariane had effectively was the rocket, when it tilted, it self-destructed. The people on the launch pad realized it was going off course. Obviously, you don't want it to go on too long. It might hit a populated area or something terrible like that. So they hit the button and blew it up on purpose. Now, the reason that occurred was because you've got lots of software on that rocket, and there was a piece of software whose purpose it was to basically compute the velocity of the rocket when the velocity of the rocket was going, and pass the velocity of the rocket to another system, and the other system was basically doing sideways stabilization of the rocket. So you just basically got simple input and output. A number is being given from output from one system, input to another. The problem that occurred was on Ariane 4, both of those were 16-bit, right? 16-bit input system talking to a 16-bit output system. They knew what the number was. What they did when they went to Ariane 5 was they upgraded one of the systems. And the number that was going up, sorry, I got that, explained that slightly wrong. What happened was in Ariane 4, there was no possibility that number was going to overflow. What happened in Ariane 5 was because the rocket went faster, the number got bigger sooner, and it overflowed the 16-bit. It basically became a larger number. It was no longer less than the 65,000. So it overflowed. And because it overflowed, it walked into the next area of memory. And the next area of memory basically gave unpredictable results and crashed it. And then it started basically ripping the rocket off. Now, the fundamental problem was when Ariane 4 was first built, they could have had exception handling code to deal with this, but they knew it was never going to happen. When Ariane 5 came along, they didn't revisit that and they didn't put that back in. So your basic problem that you have is something that was designed at one given point in time now breaks because you go forward into a newer point in time where things are getting faster, things are getting bigger, and the initial assumptions no longer apply. Because Ariane 4 was a slower rocket, you've now got a much bigger rocket getting much heavier stuff, going much faster into space. That's the first mistake that they made. The second mistake that they made was this software is not actually required to be running when the rocket has launched. The software was actually only required pre-launch because it was only required when the rocket was on the launch pad. Once the rocket had launched, they could have switched that software off. That number would have just, reset or not gone up. It would have, it wasn't a number that was being constantly incremented. The problem was that the reason that they didn't switch the software off is because of it's a difference in the mainframe between kind of cold start and warm standby and things, is that they leave it running during the launch sequence, because if you stop, if they start doing a launch sequence and stop it and have to restart it again, if they stop every single piece of software that they have to do, they have to restart more. So what happens is that feel like hot standby, it's been kept around on anticipation that if a launch is stopped, the launch has to be restarted. So it wasn't even needed. So it was counting something that wasn't even needed, had no value, even if something had gone, some particular piece of code had happened. It was left running, and it was going to be switched off 40 seconds after the rocket had got into the air, and it crashed at 39 seconds. So it was 1 second. If one more second had happened, or the number had not overflowed for another 2 seconds, the software wouldn't have been running anymore. So, and here's a picture of the progressions. We've got Ariane, these are the Ariane rockets being built, and you go from 16-bit computing, you've got 64-bit computing here, you've got larger numbers coming in, you've got this mismatch, and you've got software. So what's interesting about this? Arithmetic. So I was trying to bring this back to mainframe. So COBOL, for example, is a very, very good language of doing arithmetic, right? You cannot lose precision in COBOL, right? You just declare things and it just works. It's very good for counting numbers. a lot of mainframe software now is moving towards more modern languages like Java or Node or Golang or Python and things like that. Those have numbers. Those are, you have type numbers. You have int, you have floats, you have doubles, longs, shorts, and things like that. Now, the problem with those is if you don't know how big that number can get to, if you don't know, so you start getting data from COBOL, you start getting data from a VSAM file, you pass it to a Java program, and it might be that the Java value that you've assigned, perhaps a double or a short or something, can't actually store that number, or it can't even store the precision that you have with that number. So understanding arithmetic, it's the one thing. If you learn 3 things from this talk, if you learn one thing, it's very, very important to understand arithmetic and really do basic arithmetic. So it can be catastrophic. So if you think about those numbers that I showed, ones and zeros, how you can store, how do decimals get stored, right? If you ask yourself the question, how does a decimal get stored? You can't store every single decimal place in a number, right? Assumptions have to be made. So the way that decimals are stored in numbers is you have a mantissa and an exponent, and it's always stored as something to the power of something else. So every large number that has to be stored has to be turned into an equation of something to the power of something. And you also have to know where the decimal point is, the precision. Now, not every single number, there are gaps in that number sequence. There are holes in that number sequence. And there have been some quite sort of high profile problems to do with this. So one of them I've got at the top, it was during the Gulf War in 1991, a Patriot missile just missed its target. Its target was an incoming Scud missile. And because of that, the Scud missile basically killed 28 sort of coalition soldiers. Another one was Microsoft Excel. I don't know if folks remember, Microsoft Excel had to issue a patch recently because there was I think it was a stock market defect where a trade had occurred. Again, because Microsoft Excel was storing numbers. It was I think it was Excel 5, and it was storing numbers based upon, again, 16-bit number, 64-bit, a 64-bit floating point number. You can store very large, but 16-bit floating point numbers you can't. And again, there was a calculation that had been wrong and a stock trade that had gone wrong as well. So Microsoft had to patch that. Because we always think that every number can be accurately stored and every number can sort of be accurately grown or accurately have another number added to it and come up with the exact result. That's just not the case, okay? And I suppose the other thing is in the general thing, if you think about it, if you think about Ariane 4 going to Ariane 5, and I often see this with software being upgraded and stuff. So whenever anything is built, it's always built with a set of assumptions. And the set of assumptions they had of Ariane 5 were perfectly well tested. Right? They validated this, they had code walkthroughs, and they managed to prove that everything was fine, everything was tickety-boo. But then it's so easy to take software that was built for a particular set of conditions and just think, well, just because it works, I'm just going to use it. And that's not necessarily the case. There's so many things that seemed like a good idea at the time, but because of the environment that they use now, actually cause problems. So understanding daemons. So I was debugging a problem recently. It was on a mainframe. It was actually there was ZOSMF. And it was a performance degradation in ZOSMF. And the problem was because ZOSMF is based upon Liberty, which is a Java runtime. And in J2EE or Java, you can have what's called a drop-ins folder. You can have a folder where you can dynamically just drop in a new WAR file, and that Java runtime, J2EE runtime, will basically pick it up and now sort of publish new services. It's a kind of dynamic way to just introduce functionality into a running server. It's very useful at development time because you have a server running and you can just drop something in and take it out and drop it in. So it's almost like a debug way that otherwise what you have to do is stop the server, introduce the WAR file and restart it. So it's a dynamic way to add plugins. Now, because of that, what your Liberty server is having to do is your Liberty server is polling this directory. And the act of polling that directory, basically, first of all, it costs you I/O. So people look at the CPU usage in STSF and they wait for it to be 0, and it's never 0 because it's constantly polling, it's waiting for something, even though they're not giving it any work, that can incur costs. And in fact, in this particular case, what actually happened was that IO basically, it blew up. It was basically doing IO, and the IO was being logged, and that filled up a log file, and that basically brought the system down. So it's very important. That's the other thing as well. When you've got software and you're a developer, and you have all these really interesting like daemons and things that are optimized towards restarting quickly or introducing code dynamically, just don't stick them into production, basically. And that sort of happened with the Ariane 5, right? Because when they were launching the rocket, that system that basically cost them $1.7 billion or whatever it cost them, was simply not required. It actually wasn't needed to be on. It was kind of like test code. And I suppose the last point I want to make about this, don't give up. Ariane is a very successful rocket. It's had over 100 launches. A huge amount of technology in space is there because Ariane 5 stuck it there. And they're currently, Ariane 5 only has about 3 or 4 more missions to get to do. Ariane 6 is just about to go. So when Ariane 6, I certainly will be watching it live to make sure it doesn't blow up again. Hopefully they learned their lesson going from Ariane 4 to Ariane 5, when the first Ariane 5. But even if software crashes, that's what, you know, don't give up. Cool. Okay, now I'm going to move on to my next thing, which is Saturn. Okay, so we're not talking about satellites, we're not talking about rockets, we're not talking about using. Oh, the one thing about software as well, the assumption that if something used to work, it's going to work now. I see this a lot, and I worry a little bit about the mainframe tilting towards Java and Node and tilting away from its more traditional languages. And my worry is that, so Java and Node are very component-based software languages. So Node, for example, you know, you have packages, you have import statements, you have include statements and things like that. And what happens, you know, you have package.json and things like that. What happens is, as you build those, they will go to a repository and pull in class libraries, whether that's Maven or Gradle or Node Package Manager or something. It doesn't really matter which, and that's great, right? Because if that library that you pull in can do a lot of useful stuff for you, right? It's very useful. It's just a kind of, you know, object, you know, component-based architecture. The problem with that is you now are losing control over what your program really does, because what your program really does at execution will be perhaps 5 to 15 to maybe 40% of what you authored, but there's another 60% kind of in the shadows that's what you brought in, right? So that gets interesting because there's all sorts of issues about, is that going to crash? Has it got any vulnerabilities? Is it secure? Security in the mainframe is a big problem. So I'm not saying it's a bad problem, but you had that with the Ariane 4 to Ariane 5, but that was even built by the ESA, European Space Agency. It's so important, if you're using languages like Java and Node on the mainframe and tilting towards them, to really understand the kind of bill of materials and the scope of everything that goes into your final application, and to make sure that it was actually, because if you have something that was designed, built to work for perhaps another world or another place, and perhaps even not even running on the mainframe, and you're now dragging that in and running it on the mainframe, how do you know that it's going to behave the way it was designed? And a lot of those software libraries were written for, you know, ASCII, UTF-8, UTF-16 and things like that. Your mainframe environment might be running in different code pages. So I'm just exercising to saying that people have to understand the scope. And there's something very beautiful about COBOL, for example, which is the kind of like, what you write is what you get, kind of like a witty wiggy or something like that. I just made something up. But you know, what you write is what the compiler compiles. There's no secrets, there's no surprises. It just, you know, goes straight down the rabbit hole. Okay. Anyway, I'll get back to this. This is one of my favorite planets in the solar system. It's Saturn. Saturn is an awesome planet. It is the 6th planet from the sun. What's interesting about Saturn, and Jupiter, Jupiter's slightly further, they're the gas giants, right? So there's no more rocks in space. We're quite a long way from the sun here. It's very large. It's about 9.5 times the radius of the Earth. And it's a very interesting planet for two reasons. For me, one of which is it's a net emitter of thermal radiation. So Earth, for example, we absorb radiation from the sun. Saturn emits more radiation than it absorbs. There's a lot of activity going on in Saturn. There's a lot of very heavy elements in its core. It's a very, there's a lot going on. It has an awful lot of hydrogen. It's got liquid hydrogen on it. It's not a star. So a star is basically a nuclear fusion. You're basically fusing hydrogen into helium. It's sort of kind of lots of atomic explosions, and you're getting energy from that, right? Okay, and that's the energy that that we live by. So Saturn and Jupiter are not. They haven't got the mass to actually be to have that fusion going on. But there's still an awful lot of activity, an awful lot of kind of activity going on, thermal and activity going on. So it's emitting heat. So it's almost like a mini star, but it's not a star. Because what that thermal radiation does is that warms its moons. So it has 62 moons, and one of its moons, which is Titan, is actually very large. It's actually bigger than Mercury. So we always think, when you're at school, you always draw those kind of, Mercury, Venus, Earth, Mars, all of the planets. When I was at school, we used to draw Pluto on the end. They didn't do it anymore. But you draw the planets and you assume, well, those are the big animals in our solar system. Titan is bigger than Mercury. Okay, so Titan, if you were drawing it to scale, was bigger than Mercury. So this is a big celestial body, and it's the only one in our entire solar system, other than Earth, that has an atmosphere, which makes it really interesting to look at, because our atmosphere is sort of what gives us life. It gives us breathable gases, and it gives us weather systems and so forth. I suppose Venus has an atmosphere as well, but Venus is a very toxic atmosphere. Titan's atmosphere is methane, and it's a very cloudy atmosphere, and people have never been able to look inside Titan. They've been able to look at what the surface of the planet looked like. So you've got a planet with an atmosphere that's very close to something that's warming it, giving lots of heat. Sounds very similar to Earth. Obviously, it's not sort of, Earth has mostly a sort of kind of oxygen, nitrogen atmosphere. It's a different set of gases, but it'd be really interesting to look inside. And that's what occurred. A mission was created called Cassini-Huygens, the Cassini-Huygens mission. And the Cassini-Huygens mission is a collaboration between the European Space Agency and NASA. So NASA built this great big ship called Cassini. It's absolutely huge. And it's got a giant dish on it. And that dish can basically talk back to Earth. And it's very successful. If you look for Cassini, it's phenomenal what it's done. It's still actually flying around. It hasn't actually, I don't believe it's expired yet. Hasn't done its last mission. The way they got it, it took about 7 years to travel there. Is you don't point something straight into space and just say go. What happens is it got launched from Earth, and then it actually orbits, and you do slingshots. I talked about terminal velocity. If you fly towards a planet but you're too fast, what happens is it kind of sucks you in, but then the planet moves, and because the planet's is more gravitational towards the sun, so the planet's moving, the sun is being pulled by the planet, and then you go whoops and you miss it, but you get an acceleration, because it's like sort of kind of diving off a cliff, getting that acceleration, and then all of a sudden you're no longer falling because the thing that you're falling into has moved out of the way. So that's called slingshotting, and that's basically how you get something into the outer reaches of the solar system. So the Cassini-Huygens slingshotted, and it slingshotted, actually slingshotted Earth twice. It did a slingshot of Venus, and it's flying out, and it would basically meet. Here we are. So it launches in, what do we have here? We have the 1997, I think it launched. Yeah, it launched in 1997. And then basically, 7 years later, it gets to Saturn. So they built it all. Now on Cassini-Huygens, the reason it's called Cassini-Huygens, Cassini is your big probe that's flying around Saturn. People wanted to look inside, Titan. Okay. So what they did, I'll go forward because there's a nice picture of it here. They came up with a very clever idea. They thought, we're going to just drop something that's going to parachute through the methane atmosphere of Titan, and it's going to have a parachute to slow it down, and it's going to land on Titan. And as it falls down, we're going to switch on lots of cameras and microphones and see what's going on, and have a look inside the atmosphere. We're going to go under the atmosphere. And this ship that's falling is called the Huygens probe. The Huygens probe, it can't transmit directly back to Earth. Earth is an awfully long way away. Okay. What it does is it transmits to the Cassini ship that's close by, right? Because that dropped it off. And then the Cassini ship collects all of the data. And then the Cassini ship, in its own time, it's got this great sort of 3-meter dish, will send the data back to Earth. So it's a bit like, trying to think of a good analogy. It's like a sort of relay analogy. For this to work, this has to be able to talk directly to the Cassini that's in space, and the Cassini has to collect all the data and transmit that back to Earth. The Cassini is just sort of proxy transmitter back to Earth. This thing wasn't built to transmit back to Earth. It's just a very small craft. And it had about 2.5 hours to go back. Now, when this was about 3 years into the mission of the 7-year mission, this gentleman here called Boris Smeds. Boris Smeds is a test engineer at the European Space Agency. The European Space Agency are the ones who built the Huygens craft, and NASA, North American Space Agency, built the Cassini. Okay, so you've got 2 bits built by 2 different people. So you can see where it's going. It's a bit like the Ariane 5. You've got 2 different systems built by 2 different people talking to each other. He wasn't happy as a tester that they had never tested that this thing was going to work, as in the separation conditions, which is that if you've got the Cassini probe descending, the Huygens probe descending, sorry, I don't know why I keep going, Huygens probe descending, and the Cassini in space, you've got like transmit from Huygens to Cassini, Cassini collects back to Earth. He was like, you know, we've never tested this. He didn't know why it would fail, but he just had this kind of spider sense that something bad was going to happen. And he proposed a $5,000 experiment to test this. And what they did for testing it, because Cassini and Huygens are both together flying in space, what he wanted to do was he wanted to use Earth to kind of simulate the separation that would happen, but in reverse. He wanted to basically run a test. Now, initially, his test was refused. He was coming up to retirement. He was actually prepared to put his retirement fund towards this. And Google for it if you want. It's a phenomenal story of this kind of unsung test superhero. One of my conclusions of this is like, listen to your testers. If your testers have a sixth sense that something isn't going to work, listen to them. And if you have never done this before and your whole mission relies on this and it's never been done before, it's probably a good time to build an expensive test to make sure it happens. So when they did their test, it failed. And the reason it failed was because of the Doppler effect. Now, this idea that you've got one craft descending and then has to transmit to another craft in space that's close by, that then transmits directly back to Earth, has been done before. It was done on the early Apollo missions. So everybody's probably familiar with the Apollo moon landing, Apollo 11, and Apollo 11, the Eagle craft, which was Buzz Aldrin and Neil Armstrong, sort of dropped down onto the moon, and the what was it called? I think it was called the Columbia. Was Michael Collins was in the Columbia craft, which carried on orbiting the moon. So there's wonderful pictures that we got back of Neil Armstrong on the moon. Weren't transmitted directly from his camera. They weren't transmitted directly from the craft, from the Eagle. The Eagle transmitted them to the Columbia, and then Columbia, much bigger, that was the craft that ultimately brought them back to Earth, transmits them back to Earth. So this has been done before. It's been done before. It's 1969. Now we're in the sort of 1990s. So 30 years they've been doing this stuff beforehand. But it was always done with analog signals, right? Analog radio, right? To kind of, and because it was analog, what happened was, if you're transmitting to somebody and you're moving and you're transmitting a radio signal, you're going to have a Doppler effect. Doppler shift, we all know about Doppler shift. When you hear an ambulance or a motorbike coming towards you, it sort of gets louder and then it dies off. And that's because if you're if you're transmitting a wave and you're moving towards the source of that wave, that wave is effectively compressed by the time it comes to you, and then it's elongated as it goes away. That's also the sonic boom and so forth. Okay, breaking the sound barrier. So people had known since 1969 and before then that to adjust for that, you would change your frequency. So you would change the frequency that you were listening on. So you would say, well, I'm moving towards it, I've got a higher frequency sound, and they will modulate. And they've been doing this for like 30 years. The problem that occurred was with Cassini-Huygens is that the first time that they moved from, it wasn't an analog signal that the Huygens craft was transmitting back to the Cassini, it was a digital signal. Okay, the first time ever that they'd done this with digital data. Again, they were doing something that had been used successfully for 30 years or 25 years using analog signals. They just stuffed in digital signals and assumed it would all still work. It didn't work. And the reason it didn't work is because if you imagine, if you've got a digital signal, again, it's just ones and zeros. You've got troughs and peaks, and you've got troughs and peaks. You've got your speed of light, which is what you're transmitting this data at, is a constant, that's immutable. If you change the frequency because you're elongating, because you're moving apart, moving away from your source of data, or you increase your frequency because you're moving towards it, that will have an effect on the wavelength, right? Because the speed is basically the wavelength and the frequency together. So if you increase one, you have to decrease the other. If you increase your wavelength, so you've got ones and zeros, 1 0 1 0 1 0, then you've got another one which is 1 0 1 0 1 0. What happens is they're going to get out of alignment. And both Cassini and Huygens had atomic clocks on them, which are not affected by Doppler or anything. So you have a reference bit when you're decoding a digital signal that says, what is my start? And then, do I have a 1? Yes, I've got a 1, it's on. Do I have a 1? No, I've got a 0, it's off. And that's basically how effectively, in essence, you transmit digital data. But the problem is, if all of that gets stretched and elongated, your reference bit is going to get out of step, right? You're going to be looking for ones when you're halfway between a 1 and a 0, or looking for ones when actually you've got a 0, but because you're now 180 degrees out of phase, it should have been a 1. So everything basically just goes to dirt pretty quickly. Everything gets elongated. So how are you going to fix this? The first thing you would do is you would just upload a patch. They couldn't do it. The module that had this was an unpatchable module. Because they were so confident it was going to work, they didn't allow it to be patched because it had been working for the previous, ever since moon landings and before then. So their first mistake, they didn't allow their software in the field to be patched. The way they fixed it in the end was an absolute stroke of genius. It's a problem that we've always had before, was if you can't fix, if you can't go over it, if you can't go around it, if you can't go under it, you've got to go through it. That sometimes the best way to remove a problem is to just not do it, right? So your problem comes because you've got a separation velocity. There's nothing you can do apart from rewriting the laws of physics. Remove your separation velocity. So the only possible way that they could fix this, see if I've got one, is they basically, rather than doing a fly past where Cassini is flying past Titan, which is what they planned, and you drop the Huygens probe in and it separates, and at the initial mission, Cassini was then going to be hurtling off at basically, I think, 7 times the speed of sound, or some stupid separation velocity where they would be losing all of the data. They basically had to slow the craft down. So they physically, I'd love to have been a fly on the wall at the meeting where the software engineers knock on the door of the hardware people, probably all having donuts or, playing crazy golf or something, just, because their mission's been a perfect success, and say, do you mind, by the way, just spending 6 months out of all of the entire space mission going backwards? So they got to Saturn. They had to basically slingshot off Titan and Saturn itself. They had to do 2 flybys of Saturn to just physically slow Cassini down because it was going too fast, right? Then what they had to do was they had to drop the Huygens probe off 3 weeks ahead of time. So the Huygens probe goes 3 weeks ahead of time, then gets sucked into Titan's atmosphere and then falls into Titan at the same point in time that the now slowed down Cassini is flying past. And I'll see if I've got a picture. I think I've got, yeah, I've got a picture here. So the two of them are both moving such that their separation velocity is reduced to the point where they still have Doppler shift, but it's not quite as severe. They're only losing 20% of the payload. Okay. So it worked. Now, for those of you who've ever seen pictures of Cassini-Huygens, you have a look and you go, why are these pictures in sepia, right? Why do they look like they've got no color? The reason is because they lost 20% of the data. They were actually able to recode some of the software, and they basically had to say to all these beautiful color cameras, do you mind if you just don't record in color, please? We'd rather get the picture than have, so this was actually deliberate. They would have been recorded in color if all the data came through. It's a very Earth-like planet. It's a very Earth-like planet, which is good. It actually had rivers, glaciers, rocks, lots of geological features. Since then, Mars looks like it was once a very Earth-like planet. So what's it got to do with this mainframe talk? So what's interesting for me from a software geek about this talk, the first problem, they had a single point of failure, which was a disaster for them. The biggest one, if they could have delivered a patch to the software while they were in flight, it would have worked. So I see so much software now that's hard to fix. There's this whole movement now in Britain, right to repair. When your washing machine breaks down, you shouldn't have to get a new washing machine. You should be able to replace a component. And the same, I feel the same is true with software. We should be able to patch software more easily. I always get worried about it when the patch for a piece of software requires reshipping the entire piece of software, right? Software is hard to release. You have to system test everything, repackage everything. So I think good software should be patchable, or it should be dynamic as well. As much as possible, rules and assumptions should be externalized from the software, right, rather than hard coded. Often the reason you have to patch a piece of software is because perhaps a timeout value is too big, or somebody is calling something and passing in the wrong parameter to it, and you just want to change that. So there's much variety to effectively patch your software, either through changes to configuration or through the ability to start dynamically changing. And again, I've seen this go backwards with the mainframe. The mainframe used to have like ++ APARs and the ability to kind of micro release changes. And now I find that sometimes for me, it hurts me a little bit more when I see mainframe software coming back and they're saying, you know what, you just got to go from 2.7 to 2.8, and you have a look and you realize that 2.8 is actually, it may as well just be 3.0, right? It's an entire new version of software that you have to get, right? And everything comes, everything has got to be retested. And I find that microservices are a good thing to do that, again, if you can just replace a particular component. The lack of testing one, this comes back down to the Ariane 4 failure. It's really obvious looking at this. I mean, Boris Smets didn't even know, but he just had a gut feel that this was going to fail because there were so many things that were a first. There were other things that were a first that did work in this mission. It was the first time that it had it basically had decaying plutonium. What generated the propulsion thrust for this wasn't actually like a fossil fuel. A lot of satellites just burn fossil fuel in space to basically get out. Some space telescopes do more clever things with like helium and things, which is what the sort of Hubble telescope does to keep itself. But this actually had decaying plutonium on the back of it, and basically the sort of neutrons and the atomic particles from decaying plutonium generated the kind of Newtonian thrust to get this thing through space. So a lot of things were very, very successful about this mission, but it was the first time that they'd done that separation using binary data. And again, it's just a standard checklist. If you're releasing some software and you've never done something before, it's the first time you've done something, just extra special, test it, like really, really test it, really special, because you don't want to be the Ariane 5 blowing up, right? You don't want to be the Cassini thing that was going to just like lose all of the data. Okay, cool. So I'm just going to Sophie, I presume there's no questions in the chat, otherwise you'd have interrupted me. Or
No questions so far.
okay, cool. I hope that is in a way. The last mission I'm going to talk about is Mars. So Mars is our nearest planet. It's very, very Earth-like. A lot of great stuff about Mars. Certainly during my lifetime, when I used to go to astronomy classes when I was younger, people are fairly, Mars had water on it. It's got frozen, frozen poles. It's really, really interesting planet. A lot of this comes through the probes. Probes have been landed on Mars. So after some quite disastrous missions, so the two of the ones, there was a lot going on in the 1990s to try and get stuff to Mars. Okay, and there's particularly two I'm going to focus on here. There's a pair of missions called the Mars Climate Orbiter and the Mars Polar Lander. So the idea behind this is these are quite low budget missions, with about $200 million, compared to the billions were at risk before. The Mars Climate Orbiter is a satellite that was designed to go into orbit of Mars and study its climate. And it was also the advance guard for the Mars Polar Lander. So the Mars Polar Lander was designed to land near the pole, and it's a picture of what it would have looked like if it got there. And the Mars Climate Orbiter was also guiding the Mars Polar Lander down effectively. So as the Polar Lander was landing, it was going to be getting telemetry from the Climate Orbiter that was basically going to be guiding the two down. So these pair of missions were quite important missions to get to Mars, and then we would have studied the poles of Mars. Now, the first thing that went wrong is the Mars Orbiter missed Mars. And the reason it missed Mars, again, you can see this theme happening over and over again. The planned trajectory was to go nicely into orbit, and the actual trajectory, it basically just hit the atmosphere and just bounced off into space. It was measuring the density of the Mars atmosphere at that particular point in time, and it was trying to turn that into thrust. And there was very, very simple, is there was a number that was being transmitted from one system to the other. JPM, Jet Propulsion, Lockheed Martin were doing one system, the Jet Propulsion Laboratory were doing another system. One of them was in pounds per square inch, and the other one is in newtons. And 1 pound is 4.45 newtons. So what you basically had, and it's again the classic thing, like if you're ever speeding in America, right? Speed limits, miles an hour versus kilometers an hour and things like that. So just having a number, knowing that speed limit's 50 is not good enough. Just having the number, knowing it's 1 is not good enough. And that was the same thing, absolute schoolboy error. You're taking two very good systems from two very good engineering companies thrown together, and basically the Mars orbiter got lost. Okay. Now, the Mars Polar Lander is coming into Mars about 5 weeks later, and it's basically turns, and then the parachute deploys it, and it lands onto the surface of the planet. Okay. Now, when it came in later, it was part of the same. The reason I'm combining these together as well, it was part of the same payload. It was actually the same rocket that went into space that launched both of them. They were a pair, but the first one was designed to get there first. The Mars lander crashed. And the Mars lander crashed because the Mars lander had a system designed to detect how close it was to the atmosphere. Now, if the Mars Climate Orbiter had worked, that would have guided the Mars Polar Lander in perfectly. It would have got perfect telemetry. Because it wasn't there, fortunately, they had a backup system, but the backup system wasn't designed to be 100% perfect. The backup system, to know how far down it was, it basically had feet, dangly feet. And it was said, well, when the dangly feet detach, get to the planet, jettison the parachute. And you want to jettison the parachute because you don't want the parachute to fall on top of you, because then all your instruments are covered and it's a disaster. Unfortunately, what happened was as it landed, there was a storm on Mars, and it thought it had got to the bottom when it hadn't landed. So it jettisoned the parachute too early and then just free falled. And people since have taken pictures of it since. Yeah. Okay. So again, coming right back to the core, if you've got a number, you must know what that number is, right? That's a sort of obvious to any software engineer, but you'd be surprised by how often things break because of numbers. don't rely on a single source of data. And I think about this a lot, where I suppose the mainframe is good at this, but well, traditionally the mainframe is good at this, but things like high availability, building redundancy in your software is sort of important. Again, if I do a lot of problem supporting customers, you'll often find that something broke, and if the system had been built to be more resilient, that single crash wouldn't have caused something to occur. There's something we talk about sometimes in the mainframe, it's called sympathy sickness. And if you had it, the only reason that the Mars polar lander crashed was because it had sympathy sickness, because the climate orbiter crashed. And the climate orbiter crashed because it had sympathy. You have the woman who swallowed the fly, the kind of catastrophe that happened from a single thing. So it's very, very important to I've seen people who literally write try catch or exception blocks, and they get to the bottom and they go, you know what, this condition is not going to occur, or this condition is not that interesting, you know, this file's never going to get too big, I'm just going to make it very big and walk away and initialize it. And the problem with doing that is you don't know how that file is going to be used. Like log files often get full up, and somebody will write to a log file that's full up, and then because it's full up, they'll get an exception that comes back, and then they'll sit on an IO wait and keep trying to rewrite and keep trying to rewrite, and that might crash a program. And I've seen, I won't mention them by name here, but it's a very, very large bank, and I remember being on like quit-sit calls, and they call it war rooms and all this stuff like that, and that's exactly the problem that occurred. And that was a mainframe problem that occurred, and that's because the initial designer just didn't comprehend the fact that at scale that this thing would break, right? So you've got to be careful about that. Do design playbacks, do pair programming, you know, talk to somebody, talk to your cat, talk to somebody else, to go through, do that Boris Smeds and think, well, I haven't done this before. What's going to happen to the binary data if I've got Doppler shift? And it's very obvious. You can explain to most school children, right, the fact that the frequency changes and so will the wavelength, and now it's going to break. Right. So, but to have that insight, nobody has it. It's not lack of intelligence. You've just got to assume it's the first time we've done this. That's it, really. So that
was really good. Thank you, Joe. I personally really enjoyed that. So if everyone can make sure they go and give Joe feedback on that session, and the code is 4AP, or you can scan that QR code that's on screen at the moment. And the next session, so we've got a half-hour break now, so our next session is going to be at 3:30. And on this stream, we've got Brian talking about getting started with Ansible on Z.
Cool.
And yeah, we still don't have any questions, so I think with that we'll end it there. So thank you, Joe.
Yeah, thanks, Sophie. And by the way, if anybody wants to give feedback, please check the boxes that have the 9s on them. Yeah.
Apart from question 2, then it's number 5.
No. Did this meet your requirements? That was it. Is it a trick question? Here's me falling on my own sword, right? It's like not understanding that, telling you when 9 was a high number when it was a low number. Yeah.
Everything else.
And I just went into it out and stuff. Yeah, thanks, Sophie. Thanks so much. Yeah. Anyway, I hope to see some of you again soon at a real conference one day, or some of my work colleagues. And please, even if you thought that was rubbish, just let me know, because I'd like to do that talk and do it better, if that makes sense. Anyway.
Cool.
All right.
Thank you very much. Bye.